Hello. I'm Abedhak-Djamel Seriai. I'm Associate Professor at the University of Montpellier. I'm happy to be with you today. My research and teaching activities mainly concern the field of software engineering. I am particularly interested in software reuse, software evolution and maintenance, distributed systems, and mobile and Internet of Things development. In connection with these activities, and for several years, I led the research team specialized in the field of software engineering at the LIRM Alabama. My presentation concerns some challenges related to the field of software engineering. In particular, I will focus on some of these challenges: the mass production of software, an example of software modernization, and finally, some challenges related to the automation of certain tasks which remained until recently difficult to automate. Therefore, my presentation is structured in three parts. The first one concerns the presentation of the challenges of software engineering, software reuse, and finally, mass production of software. In the second part, I detail the example of software modernization approach, allowing to go from an individual software production process to mass production. Finally, in the third part, I briefly present some challenges related to artificial intelligence application, in particular machine learning, in the field of software engineering. Let's start with the presentation of the problems addressed by software engineering, which are the same as those of the software industry, and which concern all software development and maintenance activities. The software industry, which today constitutes one of the strategic sectors of the economy of many developed countries. This can be easily observed on this schema, which compare the benefit of this sector with other ones, some of which are very old, such as the automotive industry. We can easily see that software sector are placed in the third place, very far ahead of the automotive industry. As a consequence of this pre-elected place of the software industry, software engineering is confronted to four major problems. First, how to master the increasingly high complexity of software to develop and maintain. The diagram opposite shows an example of the exponential growth in software complexity in the automotive industry. This complexity has doubled more than 100 times in less than 10 years. Thus, it should be noted that without a mastery of this complexity, it will not be possible to coincide the needs or the expectation of customer with functionality of the software to be produced. The second problem addressed by software industry is how to produce quickly, thus reducing development time. This is an important issue because the acceleration of demand and their evolution require responsive development methods. Third problem faced by software industry is related to how to reduce development cost. As the software to develop and maintain are increasingly very complex, these require the development of an approach to reduce the cost of their development. Software software development who do not take this problem in consideration become uncompetitive. and so are bound to despair, so to die. The fourth problem addressed by software industry and so by software engineering concern the control of software quality in order to meet the requirement, but above all are to control the development and maintenance activity, knowing that the average lifespan of software is 15 years. Faced with these four problems, to which solution should be found, various challenges constitute the main activities to answer them. The first category of challenges is related to improving and automating as much as possible all stages of development, from the specification of the needs to the testing of the software. This is shown as green square. The second category concerns the improvement and automation of all post-deployment activities, what is shown in the yellow square. This concerns, for example, how to automate the identification of fault and how to automate their correction, how to be able to understand an existing software which does not have up-to-date documentation, to propose for techniques which make it possible to migrate software developed in old technology into new ones, to reduce technical debt. Other challenges concern the proposal of technique and method suitable for new infrastructure. This is shown in the brown square, orange or brown square. From this infrastructure and platform, we can cite the cloud with its various services, mobile infrastructure and cross-platform development, cyber-physical systems, and the co-development and co-evolution of material with software. And last, the Internet of Things with all the needs for interoperability and self-configuration. Otherwise, some questions related to the development and maintenance of software do not find satisfactory answer with conventional method and technique, that's why certain challenges are linked to the application of artificial intelligence and automatic learning to answer them. You can see that in the gray square on the slide. And last, an important category of challenges are related to the improvement and automation of software use. We can cite component-based and service-oriented, software product line, and model-driven development. It is this last category that I will detail a little more in the following. Reuse is among the important answers to difficulty of the software industry. It consists on the use of existing object or concept in a new situation. It includes any artifacts related to software development activities at all levels of abstraction. Reuse helps reduce development times and improve quality, as demonstrated by large companies such as NEC, Toshiba, and HP. This company report a development times improved by a factor of 1.5 to 2.5, and the quality improved by a factor of 5 to 10. This is a great improvement. The reuse process is based on two phases. Development for reuse. The goal of this phase is to identify the outline of a set of entities that can be reusable, create them, and finally organize them in appropriate structure like repositories, libraries, etc. The second phase is the development with reuse. The objective is to identify which entities can be reused following a specific context in order to integrate them into new products to be developed after a possible adaptation. The development of reusable entity is a key phase for the success of any desire to strengthen reuse within an organization. In fact, the number of this entity is an important criterion compared to the number of opportunities for reuse. Thus, two processes are available to produce reusable entity: the proactive process and the extractive one. The first is a process where reusable entities are created from scratch, right from the requirement specification stage. In this case, it's a question of adapting all stages of the traditional development process: specification, modeling, implementation, integration, test, etc., so that they make it possible to generate reusable entities at the same time of the development of software product. This process requires a particular organization adapted to promote reuse, where people can be delegated only to tasks related to reuse. The second process, which is the extractive process, aims to produce reusable entity, but not from scratch, but from existing software product. This involving analyzing an existing product to see if it is not possible or it's possible to extract a part from this code that can be formatted as reusable entity. This process includes several steps: static or dynamic analysis of the source code. You can see this below and the right part of the figure. Reverse engineering of the model of code or architecture. The transformation of these models into target format. For example, transformation of object-oriented model towards a services-based one. Finally, it concerns the generation of code for the new style or for new model. For example, how to transform object-oriented code to microservices one or services-based one. The phases related to development for reuse and with reuse in their proactive and extractive form embed two types of challenges in order to be able to optimize the opportunities for reuse. This includes challenges related to technical aspects and other related to the organizational ones. Regarding the technical aspect, different categories of challenges can be identified. The first one in the top here is linked to the proposal of new methods, tools, and language, making it possible to produce highly reusable entities. I note mainly domain-specific language that transparently encapsulate business and technical propriety as abstraction and genericity to promote reuse. This high-level language can be used as a basis for generative approaches. The second category in yellow color here is linked to the properties of the reusable entities themselves: genericity, composability, autonomy, etc. We can include in this category the challenges related to offering new concepts associated with new technologies to create reusable entity, such as software component, component on the shelf, service-oriented, microservices, modules, etc. Consequently, it's also necessary to propose mechanisms for the composition of these reusable entities. The third category in the blue color here, blue dark blue, is related to how to identify reusable entities, whether in a proactive, therefore by analysis of the domain, or extractive, therefore by analysis of the code and the available artifacts such as documentation, software history, and execution trace. Here, it's a question of proposing characteristic, recommendation of, it's proposing some characteristic or some recommendation, practical recommendation, some heuristics, some metrics, which facilitate the identification of this entity in existing system. Another categories of challenges is related to the mass production of software based on approach centered around variability, such as product line. You can see it in the green square here. Mass production consists of not producing software one by one. It consists at producing software in series. Like the manufacture of cars in the automotive industry, it's a question of creating chains of production of similar software, what we call product variant, based on identification of what is common and variable between these variants. I will return back to this category in the rest of this presentation. I will not detail here the challenges related to organization aspect, given the time limit. As I have just explained, one of the important categories of challenges in relation to software reuse concern mass production. This production is based on a key concept, that of product line. According to famous definition of Clement, a product line is a set of software-intensive systems that share a common managed set of features, satisfying the specific needs of particular market, segment, or mission, and that are developed from a common set of core assets in prescribed way. The example of different versions of the Windows system perfectly illustrate this concept. Each version of this system is produced from a set of components or artifacts which are common to all other versions. It can be considered as the kernel, but it also includes features and components which are specific to some version. In this case, the product line allows to define a variant generation engine, which allows to generate them according to the specification of the need. What feature we will like to be included. This way of looking at software development based on a product line has several advantages. Reduction of maintenance effort, enhancement of quality, reduction of development cost, reduction of time to market. All these advantages are the consequence of the existence of common base of reusable artifact by all the variants that can be generated by the line. The diagram or the figure that I present on this slide shows that from three similar products, the product line approach become clearly more advantageous than the development of one by one product. To briefly explain the process of building a product line, I can say that it's based on two sub-processes. The first one is what we call domain engineering, with all stages of software engineering, from specification to testing. This sub-process has the objective of analyzing a business domain in its entirety, and not just the domain of a given application. For example, studying all the domain of conference organization instead of analyzing the needs of particular application to be developed for organization of conference. From this analysis, we structure this domain into artifacts common to all probable or all possible application of this domain, and others which are optional. That means which may or may not be used depending on the application to be developed. For example, the auto notification functionality is common to all conference organization application. However, the organization of a discussion committee of the evaluated papers is optional, such as it has also the organization of question answer session between reviewer and other. This functionality, this feature, are also optional. The final objective of this process is to produce a domain variability model. I will come back to this later. A set of reusable artifacts, what we call it also assets, as well as a composition engine for this artifact based on the variability model must be provided. This process is equivalent to the development phase for reuse, but extend to the scale of an entire domain, not concern only one application. The second sub-process is what we call application engineering. This is the equivalent to the development phase with reuse presented before. The goal is to allow what we call product managing, or the actor is called product manager. We want to allow him to select according to the needs related to the variant to produce a set of features. And after this, the product line will be allowed to compose the artifact necessary for the generation of this product or this variant. Compose them automatically, systematically. This is the goal. We not develop the product, we generate them, we configure them. We note here that the reuse is not opportunistic, but it's systematic. As I explained it before, the software product line are based on the concept of future model or variability model. Briefly speaking, this is a model as shown in the figure, where all the features of the domain are given. Here it's concerned cell phone. These features can be indicated as mandatory. That means we need it in all products to be generated, or optional. That means that we can find them in some product, but not on all. We represent in the future model a set of constraints which manage the composition of this future. As constraint, we can see in the figure, exclude constraints between multiplier and weak. Strong Bluetooth are are linked by a required constraint. This area of mass product line comes with its set of challenges. It's mainly about the projection of all the challenges related to the development and maintenance of a single software product to the development of several variants at the same time. So, a first category of challenges in the green square here concern including the consideration of variability in all stages from specification to testing, including modeling, architecture, and implementation. For this, the definition of language of specific to the field of variability or specific for product line is one of the most important challenges. In the challenges of this category, is the use of concepts such as components, services, and microservices to be able to automatically generate, compose new configuration. A second category, yellow color here, is linked to taking into account variability for maintenance and evolution. It's a question of being able to evolve a future model and thus all the variant while guaranteeing the coherence of the product line. This is discovery or reverse engineering of the variability of the code in order to be able to model it in a future model. The proposal of static and dynamic code analysis techniques suitable for configurable code are also among the list of these challenges. Taking into account changing needs require considering dynamic variability, what we can show here in the gray square, what we call dynamic variability that is considered in what we call dynamic product line. Also, the multiplicity of different views to be taken into consideration for the creation of the product line require addressing the challenge of having a product line of product line, or what we call multiple product lines. The application of artificial intelligence techniques, machine learning particularly, are also among the challenges in the field of product line. This involves, for example, being able to provide recommendation to generate optimal configuration according to a set of needs of the product manager. This is shown in the clear blue here at the top of the slide. Right top. Other challenges are related to the nature of the file, of deployment of infrastructure. For example, cyber physical system. The question here is how to adapt product line to this infrastructure. In the rest of the presentation, I will detail an example of software modernization approach whose objective is to go from a set of similar products that have been developed in a ad hoc way into mass production. The starting point is related to availability of set of software product variants. But what are product variants? These are similar software that share mandatory features, differ in optional other features, and the main characteristic is that are developed based on clone and own approach. This means copy, paste, and modify techniques. As an example, let's consider an existing software product called drawing shapes. There are, as you can see, there are several variations of this software as shown in the table. This variant, which have been developed based on the copy, paste, modify technique, share a set of functional or non-functional features and differ compared to others. For example, we can see that drawing shape software 4 have 2 features common with all other variants from 1 to 6. But we can show that drawing shape software 6 have some features that other variants have not, as copy and paste. This situation is not uncommon because many components have this type of variant. For example, Linux kernel have many variants, as you can see in this figure. We can see another open source system like mobile media, which consider many variants that were developed based on copy, paste, modify. Also, a very known system which is ArgoUML, which is an open UML EDA, which is also a product variant. But what is the problem of the existence of this variant? The problem is these variants are difficult to use and difficult to maintain. To answer this problem, give answer to this and propose solution, we propose to create a product line starting from this variant. It's therefore what we call an extractive approach compared to proactive approach. An extractive approach to create product line start from existing variant, but the proactive one is start from scratch. Here we focus on extractive approach to create product line. Moving from products that were created by the copy, paste, modify approach to a product line where this product will be variant generated from the same base, require addressing the issue related to the domain engineering process presented previously. Identification or location of features, identify the traceability between features and assets, definition of a future variability model, identifying constraints related to variability, definition of architecture variability, and the reference architecture. It's also about create an asset integration engine. The role of this integration engine is to propose to compose all the artifacts that are identified and are created during the first phase together to generate new product. We can distinguish two methods: annotation integration and composition integration. We have future EDE tools is one of the tools that use it for annotation integration. Future house tools is one of the tools used to composition integration. Let's take a close look at the problem of future location or future identification from source code. Here, the problem is how to identify the futures, the implementation of futures by analyzing the source code of existing product variant. A future here means any distinctive characteristic of the variant. It can be functionality or quality characteristic such as performance. Our first idea to identify those parts of code that implement future is to split the initial search space. The search space here is all the source code of all the variants that are available to be analyzed. We split this initial search space in sub search space. Our goal is to enhance the quality of our search of the implementation of futures. One of the problems here is to answer the question how to split the code in sub-search space. The code fragmentation that we propose is based on the exploitation of the properties of commonality and variability of futures. Common futures have their implementation in all products, and variable or optional futures have their implementation in some products, but not all. Based on this fact, we propose the following process. First, we statically analyze source code. We extracted all OBE, that's mean objective building element, all the element of the code, class, methods, attribute, and so on. We used our classification method to distinguish common code from variable or optional code. And this will be our sub-research space. In each sub-research space, common in one hand and variable in the other hand, we apply lexical and structural similarity technique to be able to cluster some element of source code in each of the sub-search space together to have what we call atomic blocks. Each atomic block will correspond to implementation of one futures. As I have explained, our approach is based on distinguishing sub-research space related to commonalities and sub-research space related to variable code. To do this, we use a technique, a clustering technique, which is formal concepted analysis. This technique is FCA, formal concept analysis, applied on a set of objects having common properties and other not, generate what we call a lattice. To explain each more precisely, each concept in the hierarchy that is generated by applying formal concept analysis, it represents the object sharing some set of properties. Each sub-concept in the hierarchy represents a subset of the object in the concepts. Thus, we have a lattice here with concept where each concept is represent two parts. What we call intention, that represent properties that can be defined together, and the second part is what we call extension. These are all objects that have some property in common. Let's see this example of formal concept analysis applied to our problem of clustering source code. Here, we can see that objectives are mapped as software and properties are mapped as element of code. That's we call it OBE, objective building element. Started from this, we generate a lattice where each concept represents a part of the code. The root concept represents common code of all variant analyzes. Other concepts represent code that are variable. That means that belong to some variant, but not to all variant. And we can see in the extension the second part of concept is what the software that share the part of the code in each concept. Now that the sub-search spaces are defined, we find the implementation of future in each space as follows. We partition the intention of the concept to identify the implementation of the future. That means we take the code that is that represent the intention of its concept and we split it. We start the splitting from the root of the lattice. We find common future by partitioning the intent of the root concept. We find variable futures as the partition of the intention of other concept. How we do this? We define a function to measure the quality or the relevance of part of code to be considered as potential futures. Common future for the concept that represent common part and optional future for concept that represent variable part of the code. And we define an algorithm to maximize the quality of this function. That means we try to maximize the quality of the implementation of each futures. Based on this, we identify all characteristics of future, like encapsulate functionality, future interaction or composition, granularity of decomposability of futures, and refine them following the ISO quality model to metrics that are able to measure the value of each characteristic identified, encapsulation, interaction, granularity, and we define here. We have encoded the problem that we have defined what is gen, what is chromosome. We have defined the initial population. We have used the clustering algorithm to find some initial solution to our problem. We have defined genetic operator, selection operator, crossover operator, mutation operator to map to our problem. As the result, by applying our genetic algorithm to maximize the function that we have defined to that's maximize the quality of the implementation of each future based on the fragmentation of common and variable block, we find interesting result that about precision recall at F measure. The second step after have finding the future that's implemented in future variant is the identification of future model. To find the future model, we have based ourselves on formal concept analysis, but in another way. We consider that objects are software variant, and that properties here are the future implemented in each software variant. By applying formal concept analysis like this is what we call the formal context, where the object correspond here to all the product that the product variant available, and the properties are all the future implemented in each software, and we obtain, like it's shown in this slide, a lattice, where the root concept of this lattice represent all the futures that are common to all variants. The other concept represent futures that are optional, that mean that belong to some variant but not to all. That's starting from this lattice, we can identify which concepts are variable and which other are mandatory. To identify constraint, we base ourselves on the properties of lattice. For example, to find the nth constraint is we simply identify what are futures that belong to the same concept, and based on the property of formal concept analysis, that means that these futures belong all time to the same futures. That means that are linked with, and we do this for all kind of constraint. For example, here require constraint. For require constraint, we explore lattice from leaf to root, and to identify existence of constraint require. That means that in all paths from leaf to root, two futures are all time in the same path. That is the case for Bluetooth and strong. We cannot pass from leaf concept to root concept from Bluetooth without passing by strong. That means that existence of required constraint here. We do it for the other constraints. We obtain a future model here that represent what are mandatory futures and what other that are optional, and also the constraints. We experiment on ArgoUML use case, HealthWatcher, mobile media, and the results are very, very interesting because we obtain very high recall and precision value. Let's now, before ending my presentation, I would like to quickly mention a last class of challenges for software engineering, namely enhancing software engineering automation by using machine learning technique. The need for machine learning techniques is now found for a software engineering. It's really a real need, because some knowledge, process, practice are very complex to refine in order to automate certain tasks related to the software industry. For that, we need other technique as machine learning to give answer to this problem. Therefore, a new class of challenge has emerged to apply machine learning in software engineering. We can class these challenges in 6 categories. The first one in yellow is about applying machine learning to prediction and estimation of some property of code: quality, size, cost, reliability, defect, software release timing. That is the first kind of challenge, prediction and estimation. The second kind of challenge is related to discovery of propriety, and model. For example, how to identify program behavior based on execution trace. A third kind of application or challenge of machine learning to software engineering, it's about model and source code transformation. For example, how to map object-oriented application to heterogeneous distributed environment, or how assist software architecture in improving modularity in large program. The fourth challenge category is about generation and synthesis. How to generate test case, how to generate dynamic test data, how to synthesize program or script based on high-level specification. Another kind of recommendation is related to reuse library construction and maintenance. It's about, for example, how we can identify company to reuse based on very high abstract specification, how to help manage the maintenance of reusable component, how to assist the browsing of reusable library, and so on. The last category is about requirement acquisition. For example, how we can infer specification of system goal based only on interaction scenario provided by scaled order, or how to extract specification from software. This was all challenges of software engineering from very high level to mass production passed by reuse and enriching challenges related to machine learning applied to software engineering. My presentation is now complete. Thank you for your attention.